Welcome, welcome to part 2 of Physical Chemistry, Chapter 9. We're looking at real solutions. Now this is a little hard stuff, so get right in. Try not to take too long, too hard. So we're going to look at the Gibbs-Duhem equation. Now this one is the way to show how chemical potentials of two components, the chemical potentials of two components are related in a binary mixture. So first we got to remember how Gibbs is related to chemical potential. That we said Gibbs changes as a function of temperature with negative entropy, as a function of volume, a function of pressure with negative volume, positive volume, and a function of moles as the sum of all the chemical potentials. So if we make this purposely at a constant temperature and pressure, those two terms will drop out entirely, and we can say that, we artificially state this is a binary mixture. So there's not more than two substances. And the sum, the change in Gibbs is related just to chemical potential of the one times the changing moles first, the chemical potential of the second, the changing moles of the second. Normally this is used to calculate changing Gibbs as we go from reactants to products, but this is now, we're looking at changing Gibbs as we're mixing two components together. Not necessarily reacting them, just they're adjacent to them. Now looking at that equation, if we're just saying if we're changing the moles of each one at a constant rate in composition, we can look at, let's say that the Gibbs integrated would be just Gibbs, molar Gibbs, and this you can simplify it to, like, instead of changing moles, it'd be chemical potential 1, moles 1. Instead of changing that, instead of changing moles, potential 2. We just say the molar Gibbs is equal to the sum of these chemical potentials times their moles. So instead of a change, it's a constant times that, constant times that. Now, if we were to say then from there, this composition changes. So as you multiply d through everything there, we have to take d through both parts. So the chemical potential as moles changes, and the change in chemical potential as moles stay the same. So it's like they're not separate, we're allowing them to mix. We have to deal with this term and this term. Now, coming back from there, if we set both the change in Gibbs as 0 here and the change in Gibbs as 0 here, well, if that's 0, we can say that this whole term drops out and that's 0. And just look at this term. So they're saying the change in chemical potential times the moles of 1 plus the change in the chemical potential of the moles of 2 have to add up 0. So the ratio of the moles of each one, the chemical potential of each one changes by such a factor that it affects the moles. So they add up to 0. Now, conveniently changing the moles into a mole fraction is just going to be an easier way to look at that. But with that in mind, we see that essentially the chemical potential of each one will change. So as the composition changes throughout the solution, the change in one chemical potential will become dependent on the change in the other, which is kind of weird, but we're looking at the reason why we're looking at the colligative properties. We want to use this to look at the colligative properties. That when we dissolve a non-volatile solute, with volatile solvents, we're going to see a drop in chemical potential of the liquid. So see a drop in chemical potential. Now this we're also going to see a result of a boiling point elevation and freezing point depression, as well as a change in osmotic pressure. And this, the weird part here is that this does not depend on what is dissolved, only on the concentration. So this is a colligative property. We'll start looking at these when we talk about ideal solution. But look at here. Right here, this chemical potential change is not dependent on, there's nothing in here dependent on what this is, just on how much of the mole fraction this is this. How much of the total composition is X2 is going to tell us how much the chemical potential of that one drops. Essentially here, the boiling point's over here. If I draw the line, if the chemical potential line drops and moves that way by a significant amount, now the lines intersect at a different point. This intersects further back, meaning we freeze at a lower number. This interacts further to the right, further down. So it boils at a higher number. This also explains, looking at these graphs, why freezing point depression is always usually a large drop because of the size of the slopes, and boiling point elevation is usually a very small drop or a small change. So we're just essentially moving all these lines over because they're of how they're changing. So one thing to note, yeah, chemical potential of liquid change, meaning the solute is excluded from only the chemical potential of the liquid changes. We're going to exclude the solute from the freezing and boiling process. So we're not looking at the boiling of the solute or the freezing of the solute. We're looking at how the solution or the solvent changes. So let's look at freezing point depression first. So how do we justify freezing point depression? Well, we have to say that the freezing point chemical potential of the solvent solution must equal that of the solid of the solid solution. So that justify this. So we're at equilibrium. This solution must equal the pure solid. So this is, we're talking about solution, but this was pure solid. We're not considering the solute in here. Here, as a liquid, we're considering the solid. So now, based on an earlier equation we used, to consider a solution, we take the liquid and we modify that based on our mole fraction of solvent. So how much solvent we have, so this is going to drop down a little bit based on this fraction, RT ln x. Now if we solve for ln x, so we get this to the other side, divided by RT, we get essentially this equation. The change in this chemical potential from solid to solid. So what we did, then with this is there, we can plug in that. The chemical potential of the solid minus the chemical potential of the liquid is the Gibbs energy of what it takes to diffuse. And so this is the negative fusion over RT. So that's equal to ln x. Now we want to look at how freezing temperature changes with a mole fraction. So we don't want just ln x. So we also have to remember as we do this next step that Gibbs is a function of temperature. So we can't just ignore that. So to look at how, to do this, we need to look at the partial derivative of how temperature changes as a function of the mole fraction. So we're going to multiply the equation by the identities d of dx, dt over d, dx over dt to one side, so that this now becomes d, so d of dx to there. So we have d over dt. So we inverted that. So let's look. I'm not going to just wave my hands. I'm going to actually try to show. So if I multiply this just to one side, that's identity property. Remember that identity that gives you -1. That gives you -1 when you do that. So equals. So we're going to say, well, that. Oh wait, or is that no? Or is that identity? I think that might be the identity property. So, but basically, so what we're doing is, so we say all that to this side. So d of dx ln x. So we factor that in. But now we have dt over d and dx over dt on this side. So what we're going to do, we're going to invert that to get it over here. We're going to take this whole function, and then that becomes d over dt. And then the dt over dx just factors to the side. So now delta G fusion is equal to delta H minus T delta S. So that's going to make things a little bit easier. But we can turn that into dH over the delta H over T minus delta S over minus delta S, and just factor the R out. And just factor the R out. So essentially 1 over R H over T. So, and then how does that change as a function of T? Well, x to the -1 goes to negative x to the -2, H over T squared, and S just drops out. X to the 0, x to the 0, it drops out. Well, constant, yeah. So that drops out. And so you can factor that in and you have this. Okay. Now that's going to dt over dx. We have something we can integrate now. Oh, yeah, and then ln x over how does x change? Well, ln x, 1, it goes to 1 over x. So that's something we can do. Now, finally, from there, we can get x to the other side. So you have 1 over x dx, 1 over delta h over rt squared dt, and we integrate those with respect to t. And since we're looking at how this changes in regards to the fusion, as we go from a pure solvent to a less than pure solvent, we're integrating from 1, so you have ln x over essentially 1, which is ln x, but now you have that. So now we have what, like 1 over t squared. You integrate that, that's what? Yep. Oh, negative t to the first. So you're essentially saying 1 over t squared. We integrate that, and we get negative 1 over t minus 1 over t. F minus. Now, so basically what it is, natural log of x equals negative delta H fusion constant, more or less, over R, constant, and 1 over t minus 1 over t fusion, which is another constant. Last thing, we have to assume temperature H is T independent to avoid breaking our brains. So rearranging this guy to solve for 1 over T. So 1 over T. So we have, let's do this again. Just not wave our hands. We're going to actually, so we had ln x equals delta H over R 1 over T. So we're going to start by getting that to the other side. So we have ln x R over delta H 1 over T minus 1 over T fusion. We add, oh wait, is this a negative? Then we add T fusion to the other side. 1 over T fusion. So we're essentially solving for that. Okay, so 1 over constant minus R ln mole fraction over delta H equals 1 over our temperature change. Now here's where it gets a little strange. A little strange now, a little too late. Is we'll make a few assumptions to make this approximation a little bit easier. And I've actually checked these assumptions and they're really quite valid. Now, just work with me here. The first major assumption is that we're working with a dilute solution, that you are not having a high concentration of mole fraction. So it'll be more convenient to look at molality rather than a mole fraction. So we're going to turn ln of x to ln of little m. So to do that, remember x is moles of solvent over moles of solvent plus moles of solute. To turn moles of solvent into, and mole fraction into molality, we have to have moles of solvent on top, which is good. You're going to turn moles of solvent into kilograms of solvent. So we're going to turn a molality of solution is equal to moles per kilogram. So we times molar mass of solvent to get that into moles of solvent. Let's say molality. Let's say the mass of solvent, solute time. Let's see. I'm trying to think. Let's see. The mass of solute time. Well, molality solute. No. No, the molality solute. Molality solute times. So essentially the moles of solvent. So say we have 5 moles of solvent in here. 5 moles times the molar mass of the solvent turns us into grams per mole. That's grams of solvent. And molality is going to be moles of solute over kilograms of solvent. So we're going to have that calculator. So that's just a convenient way to look at the molality of the moles of solute. Now, with that in mind, the rule of logs says that ln x equals negative ln 1 over x. Essentially, that x raised to whatever power can be factored out. So if I factor a negative through there, we can flip that around, and that makes it a lot easier to handle. A lot easier to handle because, surprise, surprise, moles solvent cancels out. So we have a reason for doing that. 1 plus the molality of solute times the molar mass. That is really, really convenient to look at. Factoring that negative through, we have this ugly thing. Now I'm going to clear this. So clear all the ones. So this is our equation so far. It's still kind of ugly. Still kind of ugly. But you notice right there, constant, 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 constant. That's the only molality. So let's factor some of these things in. Okay. Now the next approximation, and this is the hard one, is that 1 plus molality solute times the molar mass of solvent is going to be approximately equal to molality of solute plus molar mass of solvent. That this is going to be, that 1 is going to be around, the natural log of 1 of this gives this essentially a rounding error where the rounding error is essentially the same. And this only works if the solution is dilute. But this error only becomes 5% if the molality it goes all the way up to, say, 0.1 molar. So we're making this dilute. So I've done this where I calculated, oh, here is just the number of mass times molar mass. And here's the number of natural log of 1 plus mass times molar mass. And you can see where they deviate, how they start deviating. So the blue line is just no deviation. And this is like, start seeing like, oh, how they start to deviate as you get more and more concentrated from the ideal linear. Very small deviation. And trust me, this will save our brains a lot of work. And I'll simplify to this. R molar mass solvent times molality over delta H fusion. So now the final approximation is how we calculate delta T. So we're going to say that delta T minus 1 over delta T fusion, that we can say like we're going to cross multiply those together, say, I got a note again. 1 over x minus 1 over y, we can say that, oh, y minus x over x times y. So we're going to get those together. T fusion times T fusion minus T. But so we're going to say that there's our delta T on top. And this final approximation is going to say that the temperature of the second point is so close to T fusion that it is another rounding error. We can say that is T fusion squared. There's usually such a small change. Now, the approximation introduces a little more error, but it only reaches 2.5% error with water, and water's a pretty big changer if the temperature difference is 10 Kelvin or more. So once again, if this is dilute, you're not going to see a big change in temperature. And if you don't see a big change in temperature, the error introduced is very small. So from there, multiplying the negative back over, you get delta T equals negative R molar mass solvent T fusion squared over delta H fusion times molality. So R times your molar mass of solvent times your freezing point of solvent squared over the enthalpy of freezing for your solvent is your constant K. Constant K. That is how they get those magical numbers. So if your solvent is heavy, it hypothetically has a larger KF. If it freezes at a higher point, but at a higher temperature, but it takes less energy to freeze. I'm going to freeze at a point. But usually as this goes up, that also goes up. So there's a few exceptions. There's a few exceptions for that. And you can deal with those. But that's just, I'm trying to show you the crazy ass math that has to be done in order to actually calculate your hypothetical KF. You can calculate it now. Calculate and try to figure it out to some extent. Yes, there's going to be some error because we make a couple assumptions. Otherwise, you have to use some approximations and it becomes a lot less nice. Okay. Same thing could be done with boiling point elevation. KF, but I don't want you to know, KF is made up only of solvent-dependent constants. So there is nothing in there for solute except for that molality, which is why this is a colligative property. Only depends on the solvent and the concentration. But so the same boiling point, the same math can be applied to boiling point elevation. We're going to wave our hands for this, but we can essentially say that you got molar mass of solvent, the delta H of vaporization, and now it's the temperature of vaporization. But it's the exact same thing. The only difference is that, yeah, now it's a positive number here. Now, because the enthalpy of vaporization is usually so much larger than the enthalpy of fusion, your KB is usually a lot smaller than your boiling point. Much harder to change the boiling point of a solvent. I mean, look at water. I mean, you may think it's a huge change in the temperature to go from 0 to 100, but it's actually going from 273 to 373. It's not as big of a change as it first appears, but we have a huge, huge change in the vaporization temperature. But, okay, hypothetically here, vodka is usually 80 proof, meaning it's 40% by volume. The density of ethanol is 0.789 grams per mils, and the KF water is 1.86. What is the freezing point of ethanol? So, looking at that, 40% by volume means there's shoot. Yep. 40% by volume means 40% ethanol, 60% malt. 60%. We're going to say, so 40 mils of ethanol, CH3CH2OH, and 60 mils of water. Now we're going to make one little assumption that water is approximately 1 gram per mil. So we're going to say, well, that's 60 grams. Now, this guy, we can't make that assumption. And so the actual amount, 0.789 grams per mil, 40 times 0.789 is going to be what? That's 31.56 grams. 31.56 grams. Now to get molality, you have to divide its moles per kilogram. So 31.56 molar mass is what? 12 times 2, 6 plus 16. 46 grams per mole. 46. 31.56 divided by 46. And then, of course, we're going to divide this by 0.06 kilograms. So the molality is 11.43. Concentrate. Now, delta T is equal to negative KFM. Multiply that 11.43 by 1.86, and you get a drop of negative 21.26 degrees. Negative 21.26. Add that to 0, so your freezing point is now negative 21 degrees. So you can put, there's a reason why you can put vodka in the freezer and not have frozen vodka, because we see this freezing point depression of 21 degrees. So unless you have a wicked cold freezer, you're good. I turned it into Kelvin, I don't know why, but not a big deal. Okay, so the last thing we'll look at for colligative properties is osmotic pressure. Looking at this hypothetically as a solution separated from a pure solvent by a semi-permeable membrane, where only one solvent can travel through. Now, as it goes here, remember, we're going to shift from until if only one can go through, we're going to shift until the chemical potentials are equal on both sides. So diffusion will occur until equilibrium is established, diluting the solution. Process called osmosis results in greater pressure. So this has dropped down, this has gone up, and if we stop that from going up, we create a force pushing against that. We call it the osmotic pressure. So we're saying at equilibrium, the chemical potential of our solution, temperature, pressure plus the osmotic pressure, and at mole fraction solvent is equal to the chemical potential of the pure solvent at a temperature and a pressure. So we're going to shift from this side to this side till they're equal at equilibrium. Raoult's law says that we can break down P star into you can break that down into the pure solvent, P plus P. We can say that the solution here on this side is equal to the pure solvent plus at the additional pressure plus RT ln x mole fraction. That the chemical potential has changed by the mole fraction here. Okay, so allowing us to say that essentially here, the pure solvent here, RT ln x is pure solvent here without the additional pressure. Now, because we say that Gibbs is a chemical potential is a function of Gibbs is equal to molar Gibbs, and Gibbs is a function of pressure and temperature, and we say, well, we only look at osmotic pressure at a constant T, we can calculate this guy for that changing pressure. And we go from pressure to pressure plus the osmotic pressure. Set that equal to Vm dp. So integrating that from P to P plus pi, you get Let's annotate that. Okay. So if that's just that, it just becomes VM dp. We integrate that, it becomes VM PF minus PI. And if we're going from P to P plus pi, the two pressures drop out and you get VM of the pure times pi. And so we essentially saying that, hey, VM to the pi equals negative what? Well, we're saying like, okay, plus RT ln x. X equals 0. And we're going to solve for pi. So once again, we do have to make some assumptions. And make some approximation. First one, we're going to keep making this one, is that the solution is dilute. That the moles of solvent equals much greater than the moles of solute. Next, we're going to convert mole fraction to that of the mole fraction of solvent to the mole fraction of solute and approximate this like we did in the freezing point depression. So we'll say that mole fraction of solvent is N solvent, right, N of the total moles. We're going to flip that around and use that to cancel out N solvent. So you get 1 plus N solute over N solvent. And then would say, well, that approximation, that 1 plus any number at a small concentration is going to be just negative of N solute over N solvent. So we're making that approximation. So that's a little bit of error. Once again, error is only 2.5% if the moles of solvent are 20 times greater than the solute. As it gets closer and closer together, then it gets bigger. But so with that in mind, so VM times pi minus RT N solute over N solvent, we get that to the other side. So get that to the other side. So you get, well, VM pi over RT N solvent over N solvent. Then we divide both sides by VM. So now remember that N times V sub M turns a molar volume into just a regular volume. So when you divide both sides by VM, you get the N over V. And that's where you get, that's how we get the pi equals RT M. Or in this case, we use C for concentration. So that's the magic we do. This is known as the Vant Hoff equation right there, the osmotic pressure equation. I think we're stopping another slide. Okay, yeah, we're stopping there. So we're just using this as a chance to look at these basic equations. Next video, we'll look at real solutions, and that's when we start to see some real problems. For now, we're going to stop it here.